Hi, everyone. I'm Ryan Castellucci. I am here to talk to you about TCPIP, which is a very complicated topic. This is going to try to be a short version. Having basic networking knowledge is very helpful in InfoSec, but the amount that you need to know is nowhere near the bookshelf worth of books that you need to know to be a network administrator. These are a couple of books that are pretty well known for TCP/IP. They're both quite large, and that TCP/IP illustrated book is volume 1 of 3. The goal here today is essentially this: distill down things in an opinionated way to the most important parts. I love this for TCP/IP. All models are wrong, but some are useful. I thought I got rid of that. So typically, when networking is taught, the OSI 7-layer model is used. So there's some issues with this. You may be thinking to yourself, wait, why are file formats here, and what the heck are NetBIOS and ASN1? And this is an excellent point. And if you aren't wondering what ASN1 is, I'm sorry. I like to think of it more like this. The definitions of layers 5 and 6 were always kind of fuzzy. The only thing we really know for sure about them is that TLS belongs in there somewhere. Ironically, TLS stands for Transport Layer Security, even though it's not on the transport layer. So I call that layer 5.5. And that frees up a layer, so we have JavaScript layer at layer infinity. Let's talk about layer 1. You have bits. Layer 1 gets them from place to place. Common things here: Ethernet with wires, 802.3. Ethernet without wires, 802.11. DOCSIS, which is what cable modems use. Various flavors of DSL, which is trying to get the best performance we can out of old twisted pairs that are in the ground and on the poles. V90, V92, those are old dial-up standards. If you use those, I'm sorry. RS-232 is serial networking. There are exotic things like RFC 1149, which is, of course, IP over avian carrier. And somebody even ran TCP/IP over bongo drums once. Quite literally IP over avian carrier. You write the data to storage media, put it on a pigeon, and have fun. A group of Norwegians actually implemented this almost 20 years ago, and they ran some pings over it. So the ping times were on the order of an hour or two, and there was lots of packet loss, and the packets didn't arrive in order, but some of them arrived, which is pretty cool. And then there was TCP/IP over bongo drums. You can run Ethernet over just about anything if you're brave enough. So the way this worked is it had some solenoids that would hit the drums and some microphones to pick up the drum beats, and it would encode data in that and decode the data and basically just be very silly. So practically speaking, that's not what anybody ever uses. So there was, on very old Ethernet, when we were only shipping around a few million bits a second, a scheme called Manchester codes was used. So you have a clock at twice the rate of the data. You XOR the two streams together, and you just send that down the wire, and that works fine for a few million bits per second. The XORing the clock and the data together makes sure that you have frequent enough transitions between high and low voltage that receivers can lock onto the signal and decode it properly. Nowadays, not going to work. Nowadays, we're sending a few billion bits per second, either down a wire or over Wi-Fi in the air. And having anything at all working in the air is miraculous, but hundreds of millions or even billions of bits per second is just magic. This is a diagram representing an older standard that is less complicated for running various signals over Ethernet and Wi-Fi. This is orthogonal frequency division multiplexing. I don't know how it works. I cannot explain it. It is magic. So let's talk about frames and packets. Packets are our layer 3 or network transmission units. And then frames are the layer 2 or data link layer transmission units. A frame usually has exactly one packet in it. That's not always the case. You can have multiple packets in a single frame, or you can have a packet that's broken up into multiple frames. There's things like asynchronous transfer mode, which has tiny frames. I think they're like 43 bytes. So you have to split up a packet amongst several of them. And frames inside frames, packets inside frames, tunneling is all pretty common. And in casual conversation, people get a little bit loose with the definitions here. Packet is sometimes used to refer to frames. It's not a big deal, just be aware of that. Okay, types of transmission. When we are on a network, we might want to talk to a specific host. We might want to talk to a group of hosts. We might want to talk to all local hosts, or there's something kind of interesting called anycast, which is where, as far as you're concerned, you're talking to a specific host, but the address that you're talking to exists on multiple servers on the internet. So routing protocols will just get you to the closest one. This is really useful for things like DNS, where it's at such a low level that there's no way to do distribution to a nearby service at a higher level. So if you ping, for example, 8.8.8.8 or 1.1.1.1, Google and Cloudflare's public DNS respectively, you should generally see a pretty fast response time anywhere you are in the world. And if you ran a trace route, you would generally see it pretty close. And that's because those IP addresses have many locations in the world where they're active. And this is great because it's fast. Layer 2, data link, that's all about local host-to-host communication. So this is when two hosts within the same logical network want to talk to each other, they can do that over layer 2. Ethernet is the most common layer 2 protocol. There's some other protocols that operate alongside Ethernet on layer 2, such as ARP and Network Discovery Protocol. A special call out here is point-to-point protocol, which can run over many different things. Originally, it was a common dial-up protocol. Nowadays, you sometimes see it running over DSL. I'm not actually sure why anybody likes to use PPP over Ethernet for DSL, but it's still somewhat common. Less so than it used to be, but it's still a thing. And then there's layer 2 authentication protocols. So if you ever see WPA Enterprise on a Wi-Fi configuration screen, that's 802.1x. This is using something called EAP over LAN, EAP being Extensible Authentication Protocol. This can be used to authenticate client devices with certificates or passwords or, well, anything else you care to write software for. This is also used on enterprise wired networks occasionally, so that somebody can't walk up and plug a laptop into a network port in the building and get anywhere. It works. A lot of places that deploy it end up having a lot of exceptions because they'll run into the odd device, usually printers, that do not want to speak 802.1x and have to have exceptions. So pro tip, if you're doing a physical pen test at a place that has this, use the printer port. Ethernet has been around since the 70s. In the very early days, it operated like a chat room. Every message was sent to every other host. This works fine when you have a couple computers on the network. You've got 5 computers. Yeah, sure, that works fine. When you have a lot, you get a crowded bar situation. People have to repeat themselves all the time. They can't hear each other. All sorts of problems. Modern networks use switching to resolve this problem. So there's a couple kinds of devices that do switching. There are switches and access points. They keep track of what layer 2 address is where, and they will selectively forward those systems only the data that they need, and also the broadcast traffic. Well, unless some jerk decides to run a CAM table overflow attack or MAC flooding attack, which causes the switches to run out of memory and start sending things out on every port because, well, at least maybe things will get where they need to go then. Another issue you can have with networks is loops. If you plug an Ethernet cable into 2 ports on a switch, you'll get what's called a broadcast storm. So it'll start off slow, but as soon as one computer does anything that requires broadcast, that packet will start looping around through that cable. And pretty soon that traffic will take down a good portion of your network unless you have something in place to mitigate it. Spanning tree protocol is one of the main things to mitigate that. There's also some switches that have a broadcast storm control feature that is just kind of a kludgy way to fix this. But with spanning tree protocol, there's a process that runs that designates one of the switching devices as the root of a tree, and then it organizes the rest of the devices into the tree, and then just makes sure that if there's any loops detected in the topology, the network ports that have loops attached to them stop forwarding packets. Ethernet frames. I'm not going to talk about the layer 1 details because you'll probably never see them unless you're designing hardware. But at a very high level, the purpose here is to provide a synchronization pattern so that the receiver can lock onto the timing. So we have destination address, source address. These are MAC addresses, which are divided into a 3-byte organizational unique identifier, OUI, and then a device ID. On some networks, you have VLANs, which can include priority tags. This is used for multiplexing multiple logical Ethernet networks on the same physical infrastructure. You will see this a lot in enterprise networks. EtherType is a protocol identifier for the data. So I don't actually remember what the one for IPv4 is, but it's 2 bytes. It says whether the Ethernet frame is carrying IPv4, IPv6, ARP, whatever. Network layer. This is where we handle communications between 2 hosts, regardless of whether or not they're on the same logical network. Routers are the big thing that operates here. They will forward packets from one network to another. IPv4 and IPv6 also operate at the network layer. We don't talk about IPv5. Control messages are run over ICMP and diagnostic messages. So you get your error, your network level error messages, your diagnostic tools, and so forth. Then we have routing protocols, which are considered part of layer 3, but usually operate on top of some layer 4 protocol. The internet runs on BGP, Border Gateway Protocol. It is complicated and not very secure. There's also Open Shortest Path First, which is currently the most common routing protocol used in private networks. There's RIP. I don't recall what it stands for. It's a very, very simple routing protocol that's not super common anymore. And then there's EIGRP, which was originally a proprietary Cisco routing protocol. They opened that up, I believe, in 2013. All of them generally try to do the same thing, which is build up a consistent view of the network within an organizational boundary, or in the case of BGP, across the entire internet, and use that shared representation to figure out what path a packet should take to get to its destination. Individual routers only really have to figure out what the next hop is, but they do so by trying to figure out the best path. I'm not going to get too deep into this. I think there's a talk right after mine going into low-level packet details and sniffing with Wireshark. But the point here is they really tried to use every bit here. So you see bit packed flags, you see the fragment offset value, which is 13 bits long, so that they can use a couple bits for flags. The source IP and destination IP are both only 32 bits, which seemed like enough at the time. There's this concept of options, which really are very uncommon in practice. There's an 8-bit protocol, because why would you need more than 256 protocols? There's a checksum here, and then there's time to live, which I'll talk a bit about a bit later. IPv4 addresses are normally written as dotted quads, so that's sets of 8 bits in decimal separated by periods. You will also hear the term octet, which is specifically an 8-bit byte, because when all of this stuff was designed, you could not rely on a computer representing a bit as, or a byte as 8 bits. It might have been 7 bits, it might have been 9 bits. I think there were some really exotic things that did other strange stuff. Also, there's a bunch of weird formats that are allowed by the old Unix specification, and I don't like them. These are, in practice, mostly used maliciously, and any software that supports them should be yeeted into a volcano. Neighbor discovery. Just a second. Sorry. Neighbor discovery, you need to know the layer 2 address to talk to a host using its layer 3 address. That will either be the host's layer 2 address directly on a local network or your router's layer 2 address. This is handled through address resolution protocol. It's pretty simple. You shout out to the entire network, hey, who has this IP address I want to talk to? And you get a reply back. There's no security baked into this, so you can just say, hey, everyone, I'm the router, please send me your packets. And most of the network will just do it. This is problematic. There's a bunch of security tools that can detect this. There's not really great solutions for actively preventing it, aside from fancy enterprise switch level filtering. And even then, somebody's probably only going to bother deploying filtering to prevent people from impersonating the router. Let's see. Provisioning. So if you want to talk to a network, you need to have an address on that network, and provisioning is how that happens. IPv4 automatic provisioning is almost exclusively via dynamic host configuration protocol, DHCP. Client devices shout out to the entire network, hey, give me configuration, and they will basically accept the first response they get. Again, no security baked into this. You can do some filtering on fancy switches. And DHCP is also a common thing for people to accidentally break in networks. There's basic stuff that's almost always done. IP, subnet, router, DNS addresses are configured via DHCP, but there's a kitchen sink worth of other features there. I was looking up the spec today and saw quote of the day server as one of the options in the DHCP specs. I got nothing. And vendor extensions can be added to do basically anything you want. Oh, I will note that dynamic DHCP is technically layer 7, but we're talking about here because it's pretty important for configuration. Long ago, when I didn't know any better and nobody was around to stop me, I was working at a wireless ISP, and I was homebrewing OS images for homebrew access points, and I wrote some terrible code that configured them when they were plugged into the network via DHCP. It would set the network keys, the network name, everything via DHCP. And it worked surprisingly well, but there are much better solutions. Okay, IPv6. IPv6 is a bit of a sore spot for a lot of people. It's been around since the late 90s, and global adoption is currently at about 30%. 1% was only hit 7 years ago. This solves the problem in IPv4 of there not being enough addresses. So you have 128 bits in an IPv6 address to play with, which is pretty cool. Instead of getting one address on IPv4, if you're lucky for a residential user, you get about 18 quintillion on IPv6. And some providers will give you even more. This is what IPv6 addresses look like. The full form is up top. You have colons separated hexadecimal in 16-bit groups. There's a canonical form for this, which is a shorthand. It is, well, use somebody else's software that already handles it. Let's put it that way. You drop leading zeros, and if there's a run of multiple groupings of all zeros in a row, you collapse them. You just leave them out entirely. There's also fun things like IPv4 mapped IPv6 addresses, where you embed IPv4 addresses in IPv6. This is for convenience of software. This does not belong on the wire. Neighbor discovery is part of ICMP. They don't use ARP in IPv6, but it works basically the same as ARP and has basically the same vulnerabilities because, again, developed in the 90s. Provisioning. The primary way to configure an IPv6 address is this magic thing called Slack, not to be confused with the chat app. Router advertisements are sent out regularly from the router on the network. They'll include the network ranges that are in use on the network, and in some cases it'll have DNS server information. It doesn't have all the features DHCP has. Hosts will then, if using Slack, they will self-assign, either picking their IP address based on the MAC address in a reversible mapping, which some people got upset about because it makes it really, really simple to track you even when you roam between multiple networks. So we have privacy extensions, which work by generating a new pseudo-random IPv6 address for your system every couple of hours. And this works fine because there's 18 quintillion addresses available on the network. So the chances of collision are low, and there's something called duplicate address detection to resolve it if it does occur. In DHCP-v6, since we often don't need to provision the IP itself, we typically operate in stateless mode, where it's just configuring the things like DNS, NTP, whatever. There's also prefix delegation, which is really fun. If you're a residential customer with a home router, your router can request a prefix delegation from your ISP, and then rather than your router getting one address, it gets that block of 18 quintillion to use on your internal network. And in practice, your client device is almost certainly going to use Slack in pseudo-random mode with DHCP-v4 for configuring DNS and whatnot, as well as your IPv4 address, since you need that anyway. Subnetting. We'll talk about this really briefly. One of the key things to be able to do with a computer network is to divide it into smaller networks. This is called subnetting. Subnet information is usually written in CIDR notation, classless interdomain routing, which is used to indicate which part of the address are network bits and which part of the host bits. the number after the slash is the number of network bits, and they are on the left-hand side. There's an example here. You can use this to determine the base address for the network and the broadcast address for the network. And it works the same IPv4 and IPv6. IPv6 just has more bits. Classful networking is obsolete, but you may see people use the terms. Class A is /8, Class B is /16, Class C is /24. Okay. So this is all complicated, and we need ways to deal with it when it goes wrong, or when people are being jerks. So whois is used to look up who's responsible for an IP address. There are command line tools available for most operating systems. There are web gateways for this. You shouldn't have any trouble finding this. There's also whois for domain names, but this has been aggressively scrubbed over the last couple of years. So you probably won't get much useful information out of it anymore. But for IP addresses, individual people don't own them, businesses do, so there's much less need for privacy there. Here's a whois report on 1.1.1.1. You can see it says it is Cloudflare is responsible. It has an email address for sending abuse complaints to, and some other metadata. Next in our troubleshooting toolbox is ping, which uses a ICMP echo request. You get an echo response back, which shouldn't be surprising. Ping tools will show packet loss, round trip statistics, that sort of thing. You get command line options to vary the size if you are thinking maybe there's some size related problem on your network, or if you're really, really unlucky and you have a data pattern dependent issue, ping tools will also let you change the pattern of the data set. Sample output from ping right there. Traceroute is really fun. Both IPv4 and IPv6 have time to live values. This is decreased at each router so that if the packet gets stuck in a loop, eventually the TTL will hit 0 and the router will know, well, I can just drop this on the floor. It will send an error message, usually, sometimes, if it isn't filtered. And this works with almost any protocol that runs over IPv4 or IPv6. Quick trace route to Twitter. Here is my example. Twitter is running, I'm actually not sure if this is doing DNS-based trickery to give me an IP that's close, or if that's an Anycast address, but I love having a fiber connection. Tunneling in VPNs. Simple example here is you just wrap an IPv4 packet in an IPv6 header so that you can get IPv4 traffic over a network that only supports IPv6. There's also Ethernet and IPv4, which is usually used using something called GRE. Then there's stuff where you put an IPv4 packet in, say, a UDP packet. Linux calls this foo over UDP. Plays nice with firewalls and hardware acceleration. VLANs, multiplexing, I talked about that before. Don't wrap things in TCP. Search for TCP over TCP if you want to know why. VPN, basically the same thing, but it's encrypted. I will summarize this as people have strong opinions about whether you should or should not use a VPN all the time. Don't use a VPN all the time. Useful for bypassing some shitty network behavior or to access corporate resources behind a firewall. Every network has a maximum transmission unit. That's the biggest size of packet that can be sent over that network. There's something called path MTU, which is the smallest MTU between you and the destination. It works with ICMP error messages. Terrible things happen if it's not working correctly. Transport layer. So you want to represent a stream. You want to represent a stream of bytes or messages. TCP gives you a really simple stream API for your application. UDP gives you a really simple message-based API for your application. There are others, we're not going to talk about them. TCP does a lot of nice things for you, makes sure everything's in the right order, retransmits any data loss, and make sure you don't overwhelm the network. UDP doesn't do any of that. So TCP and UDP both have a concept of port numbers. There's 65,000 of them. There's a registry where services can be publicly registered to different ports. So, for example, port 80 is HTTP. You get a bidirectional pipe for your application. The connection establishment is what's called a three-way handshake. You ask the server to open a connection, server accepts, you confirm, conversation occurs. This can be closed gracefully with a FIN, or you can just abort the connection with a reset packet. And your speed is limited by what's known as the bandwidth delay product. A great example of this is actually the IP over AVN carrier. You can strap a 1 terabyte SD card on a pigeon, but it's going to take 2 hours. And if you lose data, you're going to have to resend it, and your throughput is limited by that. UDP is technically connectionless. You don't have a handshake to open a connection. It's really low latency compared with TCP and requires minimal resources to implement, so it's nice for embedded devices. DNS uses it, DHCP uses it, VoIP uses it, video games often use it. I mentioned earlier IPv4 only has 32 bits in an address. That is not enough, so we give users private addresses and track state. These private addresses are not globally unique, so you have no end-to-end connectivity. On personal networks, like your home network or your corporate network, you can do what's known as port forwarding or use universal plug and play to get some incoming connections. Doesn't work on ISP level carrier grade NAT. And there's a bunch of hacks to work around it. Stun, turn, UDP hole punching. Very complicated topic, and that's all I'm going to say about it. TLS is the S in HTTPS, provides encryption and authentication of application level data. It's nice because it can be reused among multiple protocols. So HTTP uses it, but there's a bunch of other things that use it as well, like a lot of the email protocols use it. This has gone through a lot of revisions due to a long series of bugs. It's better now, mostly. There's been a lot of work done by Cloudflare and Google to make it fast and smash as many bugs as possible. The trick for encryption here is asymmetric cryptography. Servers have a certificate it's issued by a certificate authority, and your computer will have a series of certificates from certificate authorities to verify the server certificates. Application layer, HTTP absolutely dominates. If you're building an application and it's just so easy to implement it on top of HTTP. There's so much good software to support it. There are a few use cases where it doesn't work well, but HTTP2 and WebSockets fix a lot of that. So I expect it to be even more overwhelmingly popular in the future. SSH, email, SNMP, DNS, all layer 7 protocols. SNMP is used for monitoring network devices. Again, a lot of content. I don't have time to talk about it. Proxies are different from tunnels and VPNs in that they receive and then retransmit the data rather than encapsulating it. They usually operate near the client. HTTP is designed with proxying in mind. HTTPS, you have to do man-in-the-middle decryption to do a lot of the nice proxy things, but you can also just forward the bytes. Services such as any big CDN often operate what's known as a reverse proxy, which is where the proxy is on the server end of the connection rather than on the client end of the connection. Really, really common with HTTP. There's also SOX proxies, which are mostly used for naughty purposes, and Tor. They forward the connection without caring about the protocol. They forward the bytes without caring about the protocol. And there are application-specific proxies for all sorts of other things. Okay. DNS causes lots of problems when it breaks. Usually it works, but weird stuff happens when it breaks. This is what is turning a domain name into one or more IP addresses. It operates as a hierarchical distributed database. There's a set of root servers at the dot level run by independent operators. Then you have top level domains, .com, .net, .org, whatever. And then the special use TLDs, which don't, well, ARPA is part of DNS. .onion, for example, is not. .local is weird. Again, it's a quite old protocol, so you have bit packing. This is what the DNS packet structure looks like. You generally don't need to worry about this unless you're using Wireshark or something like that, and then it's interesting to know. But it will be decoded for you. So there's a couple different types of DNS servers. There's a stub resolver, which is running on your machine, doing caching for you to improve performance. And then there's a shared caching resolver. This will be running on your router or at your ISP or one of the public DNS servers operated by Cloudflare, Google, OpenDNS, etc. And then there's authoritative servers, which hold data for specific domains. So, for example, there's an authoritative server for my domain that knows all of the records that belong there. And if somebody doesn't have it cached, they can look it up there. Typically, the caching resolver will do this automatically. And there's reverse DNS. So if you have an IP and want to know the name for it, you use reverse DNS. This works by reversing the order of the IP and then looking it up in the inaddr.arpa zone. Then there's the IPv6 version, which I hope you have software to handle that for you. There's a bunch of extensions to DNS. There's DNSSEC. There's DNS crypt, which is mostly about communication between recursive caching resolvers and end users. There's eDNS0 extensions. There's DNS over TLS, which is exactly what it sounds like, and DNS over HTTPS, again, exactly what it sounds like. DNS breaking. I actually came across this post on Reddit a week or two ago. This is actually like a brilliant description of what bad DNS sounds like. This person complained that pages had to warm up And well, I like to help people. So I told this person to try using different DNS servers, and that fixed it. ISPs running bad DNS is a really common problem, unfortunately, especially ISPs that are not massive mega ISPs. There's lots and lots of other things that go wrong with DNS. Trying to log into a system via SSH and it just kind of sits there for a while reverse DNS times out. Email is broken, but only to very specific, strict, picky servers. I found a DNS misconfiguration on one of my domains that had been present for years, and I finally, after years, got denied sending email. Then don't ever be an email server admin. Accidentally changing DNS records without realizing it, really common. DNS entries not being deleted that point at cloud servers, and then those IPs are reallocated to somebody else and naughtiness occurs. Stale DNS cache entries. DNS is cached for performance. Sometimes that cache does not expire when you want it to. And then there's negative result caching, where somebody tries looking up a host that isn't live yet, but then it keeps thinking it's not live because it's caching. This is a bunch of weird geo steering that happens in DNS that can go horribly wrong. So altogether, really popular interview question is, what happens if you type company's domain into your browser? This is the network version of it. There are more complicated answers, but ARP gets the router's MAC address if it's not cached. DNS query goes out. TCP connection starts to the DNS returned IP. TLS establishes, and then you have HTTP over TLS, over TCP, over IP, over Ethernet, and then you get a web page. Yay! And that's all we have time for. Let me see if anybody has any questions on Discord, if I can type my password into my other computer.
Great job, Ryan.